Hello, Algebra 2 students. Today we are going to start Chapter 3. Chapter 3 is solving linear systems of equations in two variables. Now, we already know how to graph a linear equation in two variables using the slope-intercept form, y equals mx plus b, and the point-slope form, and the intercepts form. Um, a system of linear equations is two or more equations in the same variables, also called a linear system. As you recall earlier in chapter 1, a solution was just a value that made something true. So a solution of a system of linear equations, because there's two variables, has to be an ordered pair, x comma y, that satisfies every equation in the system. Let's take a look at two examples. And in these examples, we are going to be given a point and we have to determine if it will make this equations true. A system of equations can have more than two equations, but we're going to study two equations. So if you look at example 1, our first equation is negative x plus 6y equals 7, and our second equation is 3x minus 2y equals 11. We are going to replace x in each of those equations with 5 and y with 2. And it always is good to label your coordinates so you put them in the right spot. Now let's look at the first equation. In the first equation, the first thing you need to do is put a negative sign there because that's part of the equation. Now x is what's being replaced, so put a parentheses and then put 5 plus 6 times y, and y is 2, equals 7. And then just work it out. That's negative 5 plus 12 equals 7. Work it out to the very last line until you get single numbers, and then you have to determine if it's a true statement. 7 is definitely equal to 7, so put a check mark, that's true. However, that doesn't mean that 5, 2 is a solution to the system. You must check it in the second equation. So in the second equation, we have 3 times 5 minus 2 times 2 equals 11. 3 times 5 is 15, minus 4 equals 11. 11 equals 11. We had both trues. When both of those are true, then yes, 5, 2 is a solution. So I'm going to put true, true. Therefore, 5 comma 2 is a solution. But you don't just say it's a solution without showing your work. So that's why I showed my work. Okay, in the next example, is 3 negative 6 a solution to the system? Let's check it in equation 1. So 4 times x, and x is 3, plus y, and y is negative 6, equals 6. 4 plus 3 is 12. 12 plus a negative 6. 6 does equal 6 because 12 plus negative 6 is 6, and 6 is equal to 6. Okay, in the second equation, x is 3, y is negative 6. Be really careful. You can't get careless at this point, and you can't multiply 3 times 3 first. You have to do 3 times negative 6 first. And then you can't get careless and drop the sign. 3 plus negative 18 is negative 15. And negative 15 is not equal to 15. So even though we had a true here, we had a false here. You must have both trues in order for it to be a system, or in order for it to be a solution. So, no, 3 negative 6 is not a solution. All right. The solution to a system of equations must lie on the graph of both equations. And in today's lesson, we're going to learn how to find a solution via graphing. So let's look at example 3. Example 3, where the two lines intersect, is what is going to be the solution. So if we look over here, draw a dot at the solution, and not only do you draw a dot, you label that point. So that point is 3 comma 4. So 3 comma 4 is the solution. Easy as that. Okay, now we're getting to the heart of the lesson. How do we solve a linear system using graph and check? These are the steps. Step number 1, you write each equation in a form that is easy to graph. Most students like slope-intercept form because it's easy to plot the y-intercept and use the slope to plot additional points. However, slope-intercept form is not the most convenient all the time. You might want to use standard form and then use x and y-intercepts. You graph both equations in the same coordinate plane, just like in example 3. Notice one line was blue, the other line was red, and where they met was the intersection point or the solution. Step 3, locate the coordinates of the point of intersection. And finally, step 4, check the coordinates algebraically by substituting the point into both equations to verify it is a solution. In example 3, we couldn't check it because there were no equations given to us. But in the following, on the back page of your notes, we are going to be given equations and we can check our work. And I've laid it out for you step by step and what to do. So step number 1, um, we are given the two equations, so we must solve them in a nice form. For these two, you can use standard, I'm sorry, you can use standard form and find the x and y intercepts. But honestly, it's just as easy to use slope intercept, and students tend to like it, so let's just use slope intercept. So remember, with slope intercept, you must get y by itself. So negative, subtract x on both sides. So here we have y equals negative x minus 2. Always list the x first. And also remember to put that 1 here in front because letters are not negative. And no matter how many times I say it, students still don't seem to get that. And then before we do the second equation, let's identify the slope and let's identify the y-intercept. So the slope is negative 1 over 1. Okay? And so you go down 1, right 1. And your y-intercept, or b, is 0, negative 2. Right. And instead, we can graph them separately, or we can go ahead and solve each equation. I'm going to go ahead and just solve each equation. So for the second equation, we want to subtract 2x on both sides. So we have negative 3y equals negative 2x minus 9. Divide everything by negative 3. Not just two of the things, but everything. Y equals a negative divided by negative. You don't leave the two negatives. It's positive. Same with this one. And there is your equation in slope-intercept form. Now we're going to identify the slope. So m equals 2/3. And please don't put an x there. Slope is just a fraction. B is 0, 3. Let's plot the first equation. So the first equation, you start at 0, negative 2. And then you go down 1, right 1. And I would personally, I don't even connect the lines until I see the point of intersection. So I just leave it like that. The second graph, you start at 0, 0, 3, and you go up to, since it's positive, and the bottom's positive, so you go right 3. So from this point, you go up 2, right 3. Don't have any more room to go, but we can repeat starting from the y-intercept, go down 2, left 3. So down 2, voila, here's the point of intersection. I'm going to make that dot a little bigger than all the others. And then you can go ahead and plot more just to extend your line, but you don't have to. Now connect the lines, and your intersection point is 1, 2, -3, comma 1. Please don't make a mistake counting. Those are mistakes we just can't afford to make. I'm not going to circle it because I'm going to check in both equations to see if it ends up being true. So remember, this is x, this is y. Let's go ahead and check it. So we are going to replace in equation number 1, x with -3 and y with 1. -3 plus 1 is -2, and that equals -2. -2. Okay, in the second equation, 2 times x is -3 minus 3 times y is 1 equals -9. -6, -3 times 1 is -3. Don't put negative up a -3. There's only one negative here. Okay, -6 plus another -3 is -9. That checks. Because it checks in both, 3, 1 is our solution. All that work for one simple answer, but it works. All right, now for special types of solutions, these are the number of solutions, like where they're intersecting and so on. So let's take a look at these pictures. If you look at the very first picture, you have two lines that intersect at exactly one point, and I'm going to draw that dot in. So there's only one solution here, and that's why it's called, it's exactly one solution. And that type of system is called a consistent and independent. Independent means it has, um, or consistent independent means exactly one solution. All right. In the second graph, notice those two lines are parallel. They will never intersect. In that case, there will always be no solution. And the reason why it's a no solution is because they are parallel lines. So parallel lines mean that there's no solution and that the lines are inconsistent. Okay. And then lastly, if you graph one line and you graph the other line, one is on top of the other line. So basically you don't see this, but one of the graph, this is a graph, and then here it's the exact same graph on it. So that just means there's infinitely many solutions. Those lines intersect at infinite number of points right here, right there, right there, right there, and so on. So that is an infinite many solutions, and that is called consistent and independent. So that is when you have the same line. I don't know if I said consistent independent. I meant consistent dependent. I guess you can think of it that way, as one line is dependent upon the other line for it to be the same. So same line means dependent on one another. That's the only one that's dependent. If it has no solution, it's inconsistent. All right, our last two examples. Solve the following system, then classify the system as consistent and dependent, or inconsistent. So if you look at problem A, the second equation is already in the beautiful y equals mx plus b form, but the first one is not. So what we want to do is we want to solve that for y. So we want to first subtract 6x. So we have, make that look like an x and not a y. So we're left with -2y equals -6x plus 8. Divide by -2. And we're left with y equals 3x minus 4. Slope here is 3 over 1. Y-intercept is 0, -4. Here, the slope is 3 over 1, and the y-intercept is 0, -4. Hint, hint. Okay, so let's graph either line. So the first line has 0, -4. So 1, 2, 3, 4. Go up 3, right 1. So 1, 2, 3, and so on. Okay, the second line, I'll do it in a different color. You start at 0, -4, and you go up 3, right 1, up 3, right 1, up 3, right 1. Well, look at here. Here's a line where two lines that are just right on top of each other. So it's the exact same line. So when you're graphing it, you end up with the exact same line. So remember, when it's the same line, it's infinitely many solutions. So that's the number of solutions. And part two, that would be called consistent and dependent. At this stage in Algebra 2, you should not be making mistakes on graphing and losing negatives and so on. It's just really not allowed. Okay, and then our final example in part B, we want to solve each of those for y equals mx plus b. So for the first equation, we add 4x. So that first equation is y equals, I'll put an arrow here, 4x plus 5. Always put the x term first. Okay, our second equation, you also add 4x. And this equation is y equals 4x minus 2. Okay, for the first equation, the slope is 4 over 1. Always, always, always write slope as a fraction. So you know the rise and you know the run. Our y-intercept, always write as a point where the first coordinate is 0. Second equation, slope is still 4 over 1, but the y-intercept is 0, -2. Let's plot the first equation. Start at your y-intercept, so 0, 5. Go up 4, up right 1. Guess I don't always put the arrows here. It's just habit because I know how to do it, but if you're one of those people who needs direction, write it down or go down 4, left 1. 1, 2, 3, 4. Counting 1, 2, 3, 4. Here we go. And the second equation, I'll just do it in a different color just because I like to. So start at 0, -2. Go up 4, 1, 2, 3, 4, right 1. Okay, now the hardest part is going to be connecting the dots. So let's see how I do. Oops. Missed that one, but as you can tell, those lines will never intersect. These are parallel lines, but that doesn't tell you what the solution is because solutions can either be one ordered pair, infinitely many solutions, or no solution. So this is an example where the solution is no solution, and anything that is no solution is called inconsistent. So when you're doing your homework, you refer back to your notes. You don't just take notes and then put them away. It's a great way to study is to review your notes nightly. It doesn't take very long. You don't have that many examples to go through. And it's a really good way to retain information that when it's time for test time or review, you already know the material. So that's it for all the notes today. Have a great day, Algebra 2 students.